Indefinite integrals and the net change theorem. Indefinite integrals involves the concept of an integral without having limits. And an integral without limits simply means the antiderivative. So when we say the integral of lowercase f of x is equal to uppercase f of x, and we say that it means that uppercase f prime is equal to lowercase f, what we're basically saying is that uppercase f of x is an antiderivative of f of x. So, simply put, indefinite integrals just means to find an antiderivative. For example, if I have the integral of cosine of x dx, this just means the antiderivative of cosine, which we know is sine. But we also have to add the arbitrary constant c, because if I take the derivative of sine of x plus c, we are going to get cosine of x. The integral of x squared dx simply means the antiderivative of x squared, which we know is x to the 2 plus 1 divided by 2 plus 1, according to the power rule, plus c, and this can be simplified to be x to the third power over 3 plus c. And this is true because if we take the derivative of x to the third power plus c, the power rule for derivatives say that we take the 1/3 here and we multiply it by the derivative of x cubed, which is 3x squared. And of course, the derivative of c is 0, and 1/3 times 3x squared is x squared. So indefinite integrals just gives us a convenient way to indicate that we want an antiderivative. So now, rather than having to ask for an antiderivative in words, we can simply use this symbol to indicate antiderivative. And of course, this makes perfect sense because we know that for a definite integral, for example, the integral from 0 to 1 of x squared dx, we know this is the area under the curve x squared from 0 to 1. And we also know that the way we calculate this is by finding the antiderivative, in this case, x to the third power over 3, and then evaluating it from 0 to 1 using the fundamental theorem of calculus. And this would give us an answer of 1/3. So because we use antiderivatives in the fundamental theorem of calculus, it only makes sense for a definite integral to mean antiderivative. Now, because we will be taking a lot of antiderivatives in this section, I thought I would just remind you of the antiderivatives that we know. And I won't read through all of these, but the first two properties are really important. If you are looking for the antiderivative or the integral of a constant c times f of x, remember that you can factor out the constant c outside of the integral. The antiderivative or integral of the sum of two functions is the sum of the antiderivatives. And then we have our rules. By far the most commonly used antiderivative rule is the power rule here. And this just says the antiderivative of x to the n is equal to x to the n plus 1 divided by n plus 1. This is, of course, assuming n is not -1, because if n is -1, then it becomes the integral of 1 over x, which, of course, is the natural log of the absolute value of x. And then here we have the rest of your integration formulas that we talked about in an earlier section. And finally, these last two down here, you don't need to worry about these too much right now. So now for a few examples. Suppose we want the general indefinite integral here, and we have the integral of 10x to the fourth power minus 2 secant squared of x dx. Now, just for clarity, we have properties of integrals that tell us that we can take the integral of the first function, 10x to the fourth, with respect to x, minus the integral of the second function, 2 secant squared of x, with respect to x. Additionally, numbers can be factored out of their respective integrals, so this becomes 10 times the integral of x to the fourth dx minus 2 times the integral of secant squared of x dx. And then from here, we are simply finding antiderivatives of these functions. And so for x to the fourth, the antiderivative is x to the fifth divided by 5. And for secant squared, the antiderivative is tangent of x. And then we only need to add one constant, because if you add an arbitrary constant for each of these, the sum of those constants would just be a new constant. So our final answer here will be 2x to the fifth minus 2 tangent of x plus c. Here we wish to find the antiderivative of cosine of theta over sine squared of theta d theta. Sometimes you have to be a little bit creative to do antiderivatives. So notice that we don't know what the antiderivative of this function is. But if we algebraically manipulate this, we can rewrite this as cosine of theta over sine of theta multiplied by 1 over sine of theta d theta. And then we can say cosine over sine is cotangent, so cotangent of theta, and 1 over sine is cosecant of theta. And now we just want the antiderivative of cotangent cosecant. Now, we should remember that if you have the cosecant function, its derivative is negative cosecant cotangent. So what I have here is actually the same product of these two functions, but without the negative. So the antiderivative of this is going to be cosecant, but with a negative sign. So another way to think about this is I could put a negative here, and I could put another negative on the inside, and then I could switch these around. And then we know that this, the antiderivative here, is just cosecant, and then we have the negative on the outside. So we get negative cosecant of theta plus c. So here we have the integral from 0 to 3 of x cubed minus 6x. So notice that in this integral we have limits of integration. So this is a completely different type of problem from the previous two examples, but we approach it the same way, at least in the beginning. So when we have the integral from 0 to 3 of x cubed minus 6x dx, yes, the fundamental theorem of calculus applies, and we will need to do something with these limits, but first we need the antiderivative of the function x cubed minus 6x. And we can do this in parts. So we're going to take the antiderivative of x cubed, which is x to the fourth divided by 4, minus, and then we have 6 times the antiderivative of x, which is x squared divided by 2. And now this function will be evaluated from 0 to 3. So a couple of points to make here. First of all, when you have a definite integral, there is no need to put plus c. You do not need to put a constant of integration, because if you did, it would simply cancel out anyway. I'll show you that in just a minute. But also, you want to make sure that you simplify your function as much as possible before you plug in your limits of integration. So 6 divided by 2 is 3, so it would be useful to write this as 3x squared there. And now we plug in the upper limit of 3 and get 3 to the 4th divided by 4, minus 3 times 3 squared, minus, and then when we plug in 0, we get 0 to the 4th divided by 4, minus 3 times 0 squared. Of course, both of these are equal to 0. And this is equal to 81 divided by 4, minus 3 times 9, which is 27. And we'll write that over 1. Multiply the top and bottom by 4 here. And we get 81 over 4 minus 108 over 4. And this is negative 27 over 4. So when you have a definite integral, the answer is a number, not a function. When you have an indefinite integral, the answer is a function. Now, of course, both of these are related because the function that we're referring to is the antiderivative, and you use it in both cases. Now, let's go back and talk about why you don't need to put plus c. Let's suppose you did put plus c on your antiderivative. No harm there. And now I simplify it. And now when I plug in 3, I'm going to get the same thing here, but I'm going to have plus c attached there, minus, and then when I do the second part, plugging in 0, I will have plus c attached here. The c doesn't change because it's a constant. So even though you're plugging in 3 and 0 for x, the c stays exactly the same. And when you subtract here, you are subtracting this c. And so you end up getting c here minus c, which cancels anyway. So when you're doing a definite integral, don't put plus c. It's just a waste of time and extra effort. In our next example, we wish to find the integral from 0 to 2 of this rather complicated function, and then also to interpret the results in terms of areas. So first, let's compute the integral. We have integral 0 to 2 of 2x cubed minus 6x plus 3 over x squared plus 1. Now, I feel like I should show you how to separate this integral in case you prefer to do it this way. Sometimes I show this step, sometimes I don't. In the previous example, I did not. But according to our properties of integrals, we can take the integral from 0 to 2 of 2x cubed dx minus the integral from 0 to 2 6x dx plus the integral 0 to 2 3 over x squared plus 1 dx. Additionally, the numbers, the coefficients here, can all be factored out of the integral. And if we do that, it's going to look like this. All right. And now we just have to compute these antiderivatives. So we have 2 times antiderivative of x cubed is x to the 4th over 4, evaluated from 0 to 2, minus 6 times the antiderivative of x is x squared over 2, evaluated from 0 to 2, plus 3 times the antiderivative of 1 over x squared plus 1 is the inverse tangent of x. Now, you are going to plug in 2 and 0 and subtract on each one of these. And you can do that, but I think it's easier if you actually combine all these together, so this will be x to the fourth over 2. This one will be minus 3x squared. And this one is plus 3 inverse tangent of x. And you can just evaluate the whole thing from 0 to 2. So if you think about it, there really is no need to separate the original integral into 3 problems. You can simply find the antiderivative of 2x cubed, which is this, and then the antiderivative of negative 6x, which is this, and finally the antiderivative of 3 over x squared plus 1, which is this, and then just evaluate the whole thing from 0 to 2. So when we plug in 2, we get 2 to the fourth divided by 2 minus 3 times 2 squared plus 3 times the inverse tangent of 2 minus 0 to the fourth divided by 2 minus 3 times 0 squared plus 3 inverse tangent of 0. And now we need to compute this. So we have 16 divided by 2 minus 3 times 4 plus 3 inverse tangent of 2. That's interesting. Minus, and then all of these are 0, including the inverse tangent of 0. And so we have 8 minus 12 is negative 4 plus 3 times the inverse tangent of 2. And this is our answer. And this is approximately negative 0.6786. Now, what does this mean? Well, it's a definite integral, right? Definite integrals always represent the area under the function that you are integrating. So if we were to graph this function, so f of x is equal to two x to the third minus 6x plus 3 over x squared plus 1. Let's bring in a graph of that. Okay, so here is that graph. We are integrating from 0 to 2. So if you look at the graph, starting at 0 and going to 2, you will see that the area under the curve is actually the area between the curve and the x-axis. So we have 2 pieces of area that are above the x-axis and 1 piece of area here below the x-axis. And what this number here represents is the green area minus the red area. And if you look at this graph, it does appear that there is more area below the x-axis than there is above the x-axis. And that is exactly why our answer comes out to be negative, because area below the x-axis gets counted as a negative area. In our next example, we have the integral from 1 to 9 of the function 2t squared plus t squared radical t minus 1 all over t squared dt. Once again, sometimes before you can find the antiderivative, you need to simplify your function. So let's take a look at the function. We have 2t squared, and we can write that over the denominator, t squared. And then we have plus t squared radical t, also over t squared. And finally, minus 1 over t squared. And here the t squareds cancel out. Here the t squareds also cancel out. And this is just 2 plus the square root of t minus 1 over t squared can be rewritten as t to the negative 2. And so we can re-express this integral as the integral from 1 to 9 of 2 plus the square root of t, we'll write that as t to the 1/2, and then minus t to the -2. And now from here, I'm just going to take the antiderivative of each one of these terms. So the antiderivative of 2 is 2t, plus the antiderivative of t to the 1/2 will be t to the 3/2 divided by 3/2, minus the antiderivative of t to the -2. Be careful with negatives. You need to do -2 plus 1 and then divided by that. And so that is going to be t to the -1 divided by -1. And we will evaluate this from 1 to 9. So first, let's simplify. We have 2t plus dividing by 3/2 is the same as multiplying by 2/3. And then here, the minus and the minus cancel out, so we get a positive, and t to the -1 is 1 over t. And this goes from 1 to 9. And so now we'll go ahead and plug in 9. And then subtract, plug in 1. And now let's simplify. We have 18 plus 2/3 times, what is 9 to the 3/2? Remember how we do this? We take the square root of 9 to the 3rd power. That is 3 cubed, which is 27. Minus 2 times 1 is 2. The minus carries to the next term. That's going to be minus 2/3 times 1 to the 3/2 is 1. And finally, minus 1. So make sure you distribute that negative to everything. And now let's simplify this. We have 18. 2/3 times 27 is also 18. And then we have minus 2, minus 1. And then I'll do the fractions last. So let's see. 18 and 18 is 36. Minus 2 is 34. Minus 1 is 33. Plus 1/9. And then minus 2/3, I'll change that to 6/9. So this is 33 minus 5/9. And then lastly, I will multiply the top and bottom by 9 here to get our common denominator. And then all we have to do now is multiply it out. 33 times 9 is 297, and then minus 5, and then over 9. So this is 292 divided by 9. And try not to worry about all the computations. I mean, this is just arithmetic. The important thing is, in the beginning, before you can take an antiderivative, okay? So before you can use the power rule on all of these, because that's what we did, you had to simplify your original function. One more thing before we move on. When you take a definite integral of the function f of x from a to b, you get the antiderivative evaluated at b minus the antiderivative evaluated at a. The key is this is a number, and it represents the area under the curve. When you have an indefinite integral of the same function, you now just get the antiderivative. And the most general antiderivative means you need to add an arbitrary constant. This is a function. In fact, it is a family of functions, because this arbitrary constant could technically be any number. So it's really important to understand the difference between these two things. And it's also important to understand that these are very similar at the same time. In other words, they both involve the antiderivative. Now let's talk about the net change theorem. The integral of a rate of change is the net change. So if we have the integral from a to b of some function f prime of x, we know that we get the antiderivative of this function, and of course the antiderivative of f prime is just f, and we're going to evaluate that at b and then minus evaluating it at a. So what this says is that when you take the integral of the rate of change of a function, you get the net change of the function. Let me give you a couple of examples. Suppose v of t represents the volume of water in a reservoir at time t. Its derivative, v prime of t, is the rate at which the water flows into the reservoir at time t. So if we take the integral of v prime of t from time t1 to time t2, we get v of t2 minus v of t1. In other words, if we integrate the rate of change of the water flowing into the reservoir, we get the net change of the volume of that water. So in other words, if the volume went up over that time period, this would be a positive number. If the volume decreased over that time period, then this would be a negative number. So the net change just takes the initial quantity subtracted from the ending quantity. Another very common example is this one. If the rate of growth of a population is dn dt, then if you integrate that rate of growth with respect to time from t1 to t2, you get n of t2 minus n of t1. In other words, if you integrate the rate of change of the growth of a population, you get the net change in that population. And once again, this can be a positive number or it can be a negative number. And not to sound too morbid here, but if this number is negative, it means that more people died than were being born over that time period. And if this number is positive, it means that more people were born as opposed to dying. And so this is a useful tool when studying populations. Perhaps the most famous example of the net change theorem is when you're looking at a position function and a velocity function. Suppose that an object moves along a straight line with a position function s of t, and it has a velocity function v of t, which is equal to s prime of t. So if we integrate the velocity function, the velocity is the derivative of position. So we know that's going to be the position evaluated at time 2 minus the position evaluated at time 1. So you're just looking at the net change in the position. This is called the displacement of the object. And it can be positive or negative. Just consider the very simple example. If you start here at point A and you move forward 2 units, and then let's suppose you move backward 1 unit, your final position at point B is 1 unit from where you started from. So your displacement is equal to 1. However, that's not the same as the distance traveled, because if you take 2 steps forward and 1 step back, your distance traveled is 3 units. So when you integrate the rate of change of a position function, you are getting the net change in the position, which again is called the displacement. And this can be positive or negative, because if you take more steps backwards than forward, you will end up behind where you started. All right, how about the distance? How do you calculate that? Well, to calculate the distance, what you need to do is count all steps forward as positive distances and also all steps backwards need to be counted as positive distances. Well, when you move backwards, it's naturally counted as a negative distance. So the way you make it positive is by taking the absolute value of it. So in short, when you want to find the total distance traveled, you need to integrate the absolute value of the velocity, not just the velocity all by itself. And the distance traveled is harder to compute. So I will just tell you now, this is more difficult. And it's because integrating an absolute value requires more work. Let's take a look at an example. So here we have a particle moves along a line so that its velocity at time t is given by this function, measured in meters per second. First, we want to find the displacement of the particle during the time period t from 1 to 4. So this is straightforward. To get the displacement, we are going to take the integral from 1 to 4 of our velocity function. And this will be the integral from 1 to 4 of t squared minus t minus 6. So to complete this calculation, we need the antiderivative, which I will do here without explanation. And then we have to evaluate that from 1 to 4. And so we get 4 cubed over 3 minus 4 squared over 2 minus 6 times 4 minus the quantity 1 cubed over 3 minus 1 squared over 2 minus 6 times 1. If we do the math here, we have 64 over 3 minus 16 over 2 minus 24 minus 1/3 minus 1/2 becomes plus 1/2, and minus 6 becomes plus 6. So this is 64 over 3 minus 8 minus 24 plus 6 minus 1/3 plus 1/2. And let's combine these. Let's see here. Negative 8 and negative 24 is negative 32. Plus 6 is negative 26. So we've got 64 over 3 minus 1 over 3 minus 26, and then plus 1/2. Let's see, this is 63 over 3 minus 26 plus 1/2. 63 divided by 3 is 21 minus 26 plus 1/2. This is negative 5 plus 1/2. And that is finally negative 10 over 2 plus 1 over 2, or negative 9 over 2. So what this means is that when you travel from t equals 1 to t equals 4 seconds here, this object ends up negative 9/2, or negative 4.5 meters behind where it started. So it just means that it moved backwards more than it moved forward. Now let's get the total distance traveled. So to find the total distance traveled, we need to take the integral from 1 to 4 of the absolute value of the velocity function. And this is the integral from 1 to 4 of the absolute value of the function t squared minus t minus 6 dt. Now, what's really important here is that you cannot integrate an absolute function until you remove the absolute values. So what is the absolute value of t squared minus t minus 6? What does it actually equal as a piecewise function? Well, let's think about t squared minus t minus 6 in terms of factoring. We know we can factor it into t minus 3 times t plus 2. And if I set that equal to 0, we know that it's going to equal 0 when t equals 3 or when t equals negative 2. Now, if you look at a number line, again, we know it will be 0 for these two values of t. But what about the other values of t? For example, what is the value of this expression if we plug in a number greater than 3? So just imagine if we were to pick a number like x equals 10, and we plug that in to our function here. 10 minus 3 is 7, 10 plus 2 is 12. If I multiply those, I get a positive number. And in fact, any number I plug in greater than 3 is going to give me a positive number for that velocity. So I'm going to say that that function is positive if t is bigger than 3. If you plug in a number between negative 2 and 3, such as t equals 0, when you plug in t equals 0, you will get negative 3 times 2, which is a negative number. It's negative 6. And what that means is that this function is negative for all values of t between negative 2 and 3. Likewise, if you plug in a value of t less than negative 2, say for example negative 5, you can plug that in and you will get a negative times a negative, which is a negative. And so, a negative times a negative is a positive, and so we know that it's positive here. So why am I talking about all this? Well, remember what an absolute value is. If you plug a number into an absolute value and it is already positive, the absolute value doesn't do anything, right? So if I plug in a number that is bigger than 3 or a number that is less than negative 2 into here, it's going to be positive already, which means these absolute value bars don't really need to do anything. So what I'm saying is, if t is a number less than negative 2 or a number greater than 3, the absolute value of t squared minus t minus 6 is just t squared minus t minus 6. However, if I plug in a number t in between negative 2 and 3, this is where it gets interesting. Any number in here that I plug in is going to give us a negative number, and now the absolute value has to make it positive. Well, the way an absolute value makes a number positive is it takes the opposite of that negative number. So what does this all mean? Well, when you integrate the absolute value, I have to decide which function do I have here. Well, if we're on the interval from 1 to 4, let's draw into the number line down here. 1 is right about here, and 4 is right about here. You can see for part of the interval from 1 to 4, the function is negative, and for the other part, it's positive. Specifically, if I'm looking at the function from 1 to 3, we know that it's negative, and from 3 to 4, we know that it's positive, according to our number line up above here. So what does this all mean? What I'm going to do when I integrate this is I'm going to integrate from 1 to 3 of the absolute value of t squared minus t minus 6, plus then I'm going to integrate from 3 to 4. But when we are integrating from 1 to 3, we are in this interval, and the absolute value is the opposite of t squared minus t minus 6. So this integral here becomes the integral from 1 to 3 of negative quantity t squared minus t minus 6 dt. Plus, from 3 to 4, the function is already positive, and so when we remove the absolute value, there's no negative that needs to go in front of it. To help you understand what we're doing here, I have a graph of the function v of t equals t squared minus t minus 6 right here. Now I want you to notice that when t is a number in between negative 2 and positive 3, you can see that the function is below the x-axis. that means it's negative. Okay? So that's representing this part of the definition. But if I look at the function to the right of 3 or to the left of negative 2, it is above the axis. And that's this part of the function. So what it means is when you're doing an absolute value of a function, if the inside function is below the x-axis, you have to take the opposite of that number to make it positive. And if the function is already above the x-axis, you don't have to do anything to the function. So again, when we integrate from 1 to 4, I want you to see that from 1 to 3, the function and therefore the area is going to be negative. And from 3 to 4, the function and therefore the area is going to be positive. So to get the total distance traveled, I have to take this negative area and turn it into a positive area. And that's exactly what this negative sign is doing. Okay, now let's go ahead and compute these two integrals. All right, so this first integral here, we have the integral from 1 to 3, negative t squared plus t plus 6 dt. Let's do the antiderivative first. And then we'll evaluate from 1 to 3. Simplify. And when you combine all these numbers together, you should get 22 over 3. Now let's work on this integral. First, we'll take the antiderivative. Evaluate it from 3 to 4. Simplify. And you should get 17 over 6. And so the total distance traveled is the sum of these two numbers, 22 over 3 plus 17 over 6. Let's multiply this by 2. That gives us 44 over 6 plus 17 over 6, which is 61 over 6. And so you can see the distance traveled is quite a bit more work to calculate than the displacement. And that concludes this video lesson.